Here we're going to look at how we use a temperature entropy diagram for water to determine something about an adiabatic turbine. So we're given that superheated steam enters the turbine, we're given the pressure and the temperature, and then we're given the outlet pressure. And because this is reversible and adiabatic, it means it's a constant entropy process, and therefore it makes it easy to use the diagram to determine conditions. And we want to know what's the quality leaving, and we want to know the enthalpy change in the turbine. The enthalpy change, of course, then corresponds to how much work we get out of the turbine. So here's the temperature entropy diagram. We're at 5 megapascals, and this is the pressure indicated here, and we're at 350, so this is right around here on the diagram. So that's our starting condition. Now the advantage of using a temperature entropy diagram is we draw a vertical line for all reversible adiabatic processes, and our ending condition is at a pressure of 0.5 megapascals. So we follow this line. We have to be on this blue line here. Entropy is the same as the inlet entropy, so we're right around here on the diagram. And so you'll notice these lines that correspond to constant quality. That's quality of 0.9 here. So roughly the quality is about 0.92. And then the enthalpy change, so delta 8 enthalpy change would be the final enthalpy, namely the value here. So notice constant enthalpy lines are these lines here, the green lines. So the final enthalpy around 2570. We probably can't read it quite that accurately. And likewise, the initial enthalpy is around 3070. And so this means final minus initial enthalpy change 500. This would then be converted to work in the turbine. So the idea here is that a temperature entropy diagram is really well suited to solve problems that are constant entropy.